When we think of satellites, we picture them gliding through the silent vacuum of space. But beneath that orbit lies a highly stratified, volatile barrier. Operating spacefaring technology requires solving a multidisciplinary engineering problem, bridging orbital mechanics, aerodynamics, and electromagnetic propagation, contrasting the fluid mechanics of wind shear and orbital drag with the optical physics required to penetrate deceptive cirrus cloud cover. A spacecraft never truly operates above the weather. Its survival and function are dictated by its ability to navigate these physical and optical properties. Before reaching the vacuum, a launch vehicle must penetrate the troposphere, the densest operational fluid barrier in the atmosphere. During this rapid acceleration, the primary mechanical hazard is wind shear, defined as the rapid rate of change of wind speed and direction with altitude. When a lateral gust strikes, its vector mathematically combines with the vehicle's forward airspeed, creating an instantaneous angle of attack that shifts the airflow. Because the rocket is slender, the nose cone enters this high wind region and generates lift before the aft fins. This timing delay induces a severe pitching moment. The rocket attempts to rotate around its center of gravity, creating massive bending loads that can exceed the airframe's design limits. Safely navigating these conditions requires highly accurate vertical wind column profiling prior to launch. Operators gather this data using a network of sensors, ranging from traditional tethered pilot balloons to hovering unmanned aerial vehicles equipped with ultrasonic anemometers. This highly localized wind vector data feeds directly into the rocket's flight computer, dictating immediate thrust vector control adjustments during the ascent. Aerodynamic survival relies on mapping and calculating the fluid dynamics of an invisible air mass before the engines even ignite. Once a satellite clears the lower atmosphere, it establishes orbit in the rarefied environment of the thermosphere, at altitudes up to 1,000 kilometers. To maintain this low Earth orbit, the satellite must travel at an extreme velocity of approximately 7.8 kilometers per second. This formula shows the classical aerodynamic equation for drag, defining the continuous force acting against the satellite. Notice how the velocity squared term dominates the equation over the atmospheric density, represented by the Greek letter rho. Because of this exponential multiplier, even microscopic, fractional fluctuations in that density create immediate, significant deceleration forces on the spacecraft. The primary variable causing these sudden density fluctuations is space weather, specifically geomagnetic storms, that trigger extreme thermospheric expansion. Here, we encounter a unique climate paradox. In the highly rarefied upper atmosphere, increased terrestrial carbon dioxide acts as a highly efficient coolant, radiating heat away into space. This chart illustrates how continuous thermal radiation is actively lowering the baseline average density of the upper atmosphere over decades. While the absolute peak density during future geomagnetic storms will be lower, the relative spike erupting from this newly lowered baseline will be far sharper. This steep relative gradient leads to abrupt orbital decay, creating real-world operational consequences like the unexpected loss of commercial satellite batches during solar events. Carbon emissions are altering the density baselines and drag gradients that orbital guidance systems must be designed to handle. If we shift focus from surviving space to actually observing the Earth, we face a major obstacle. Over 50% of the surface is obscured by clouds at any given time. To see through this, satellites exploit atmospheric windows, specific segments of the electromagnetic spectrum where molecular absorption by atmospheric gases is minimal. But a nuanced break exists in the upper troposphere, optically thin cirrus clouds. These microscopic ice crystals are nearly invisible to standard visible light sensors. Despite their visual transparency, these clouds heavily scatter long-wave infrared radiation, introducing a positive 1.5 watt per square meter radiative forcing error. This invisible barrier skews data, causing massive relative retrieval errors in carbon dioxide total column tracking and corrupting the models used to monitor global climate change. To solve this, optical satellites utilize a highly specific channel near 1.38 micrometers in the shortwave infrared spectrum. Because dense water vapor below absorbs this wavelength, any returned signal must have hit high-altitude ice. An algorithm uses this to digitally mask the contaminated cloud areas. Mathematical filtering via strict spectral bands is the only method to establish ground truth through these optically deceptive layers. While short-laid infrared handles thin ice, achieving true all-weather observation through thick convective storms requires active microwave sensing. The physical mechanism dictating whether electromagnetic radiation penetrates a storm or is blocked by it comes down to a mathematical distinction: Rayleigh scattering versus Mie scattering. By using L and C-band microwaves, engineers leverage the inverse fourth-power wavelength dependency of Rayleigh scattering, allowing the waves to pass through liquid water droplets without degrading. Once a satellite captures this data, it faces another physics problem: transmitting heavy telemetry back to ground stations using robust radio frequency links. Communication architects must balance the high-capacity throughput of the Ku and Ka bands against the risk of signal degradation, an industry phenomenon known as rain fade. Rain fade occurs when transmission wavelengths approach the physical size of the falling raindrops. When that size threshold is met, the system falls victim to Mie scattering, causing severe signal attenuation at the receiving dish. Both a satellite's ability to see the Earth and its ability to talk to it are strictly governed by the geometry of scattering physics. From the launch vehicle navigating extreme wind shear profiles, to the orbital platform fighting thermospheric density, to the sensors threading narrow infrared bands to bypass invisible ice, mission success relies on systems specifically engineered to endure, bypass, or look directly through the fluid and radiative properties of the atmosphere. Spaceflight is a continuous negotiation with the Earth's atmospheric gradient,